Training stand ESC,
Air LB, EDL, and Air SC. The training stand ESC is used to explain and demonstrate the functionality of an electronic driving stability control system. The term driving stability control (ESC) refers to an electronically controlled driver assistance system for motor vehicles that counteracts the car braking out by braking individual wheels in a targeted manner. In the current version, ESC is an extension and linkage of the anti-lock braking system, Air LB, with a traction control system, Air SC, and an electronic differential lock EDL, as well as an electronic brake force distribution. Air LB, anti-lock brake, prevents the wheels from locking when braking and thereby maintains the tracking forces required for steering. The vehicle remains steerable even when braking hard so that obstacles can be avoided. Better braking behavior and shorter braking distances are achieved, especially on wet roads. EDL, electronic differential lock, diverts the drive torque through electronically controlled braking of spinning wheels to gripping wheels. EDL control intervention only takes place up to a certain driving speed so as not to negatively affect driving stability. Air SC, anti-spin control, prevents the drive wheels from spinning when accelerating, over the entire vehicle speed range, by reducing the engine power in a controlled manner. ESC prevents the vehicle from skidding through targeted intervention in the brakes and engine management. The ESC uses sensors on the brakes and the steering wheel to check what the driver wants and compares it with the actual driving behavior, which is recorded by other sensors. If it detects a difference between what the driver wants and what the vehicle is doing, it intervenes within a fraction of a second, depending on the requirements. One or more wheels can be braked individually for stabilization, so that the car remains steerable and controllable. The training stand includes an MK60 brake system from Tevez, which is built into a large number of vehicles in the volume market, for example VW Golf. The ESC braking and driving stability system is one of the safety-relevant vehicle components, which is constantly checked to ensure that it is functioning correctly through extensive self-diagnosis functions. If such a system is to be operated in simulation, extensive technical measures must be taken in order to enable the most error-free operation possible. First, the following is an explanation of the components on the front panel of the training stand. The MK60 brake system receives the wheel speed information required for the control processes from 4 wheel speed sensors that scan the toothed sensor wheels on the respective wheels. No original wheel speed sensors are installed on the training stand. The sensor signals are electronically simulated and sent directly to the inputs of the ESC control unit. The 4 wheels are shown as a graphic on the front panel of the training stand. The wheel speed is represented qualitatively by 2 rotating points of light, the speed of which changes with the wheel speed. A digital brake pressure display is assigned to each wheel. If you lightly press the lower left corner of the display with your finger, the type of display, numerical value, pointer instrument or line recorder, can be selected. The brake pressure or the intervention of the ESC for driving stability control can be read on these displays. The yaw rate display is located in the upper area of the front panel, between the front wheels, corresponding to the rate of rotation around the vertical axis, depending on the steering angle and driving speed of the vehicle. Points of light move around to the left or right at different speeds. If the steering wheel is in the neutral position, the light points stand still, regardless of the vehicle speed. Below the yaw rate display there is a bar display on which the currently effective engine drive torque can be read qualitatively. This is interesting because the ESC control unit determines how large the maximum drive torque may be in order to ensure safe driving. If the torque limitation is activated by the ESC, the torque display no longer follows the actuation of the accelerator pedal. On the right below the torque display, there are 3 buttons for inputting disturbance variables. By pressing this button, faults such as oversteer, understeer and insufficient lateral acceleration values can be entered. However, this only makes sense if a certain driving speed is present and a curve is being driven. A light-emitting diode indicates when a fault has been entered. The light-emitting diode goes out when the entered fault has been switched off again by a control intervention by the ESC. Under the instrument cluster is a rotary knob that acts as an accelerator pedal and with which the simulated vehicle can be accelerated. In addition, an engine noise can be heard after starting the engine, which changes with the engine speed, driving speed. With a small steering wheel, which is arranged under the vehicle instrument cluster, steering angles can be entered or curves can be driven. Care should be taken not to apply excessive torque to the steering wheel at the end of the steering angle range in order to prevent the potentiometer, which is turned by the steering wheel, from being damaged. There is a USB socket on the left under the fuse holder. The training stand can be connected to a PC with a USB cable in order to show further measured values of the ESC system. For this, a PC program belonging to the scope of delivery of the training stand must be installed on a Windows PC. Make sure that the USB connection between the training stand and the PC is always established before the PC program is started. Otherwise, the training stand will not be recognized by the program. With this push button, the ESC or ASC system can be switched on and off. A drive torque limitation by the ESC control unit then no longer takes place. The operating voltage, terminal 15, is switched on with the ignition key, ignition lock, and if the engine is started, terminal 50, an engine noise can be heard. Attention! The operating voltage may only be switched on when the training stand has been supplied with voltage by switching on the battery isolating switch, not before. There is a multiple socket under the USB socket for connecting the student measurement circuit diagrams. If a circuit diagram workplate is connected there and a paper mask with the printed circuit diagram is placed on the plate, measurements can be carried out there with a multimeter or oscilloscope. Up to approximately 8 circuit diagram worktops can be connected. A fault switching device can be connected to this socket. This device can be used to simulate electrical faults within the ESC system. These errors can be found by the trainees either through electrical measurements on the measuring circuit diagram or an error diagnosis using a workshop test device, e.g. VCDS. Attention! If no fault switching device is connected, there must always be a dummy plug in this socket. Otherwise the device will not work because there are too many errors. A workshop test device, for example VCDS PC test adapter, can be connected to this OBD socket. This makes it possible to delete the error memory of the ESC control unit. Since errors can occur after some time in simulation mode, real-time measured values can also be displayed in this way. This is important, For example, to be able to set the 0 point of the steering angle for the simulation. A battery isolating switch is located on the lower right edge of the front panel of the training stand. This switch disconnects the supply battery from the electrics of the training stand when the training stand is not being used. This prevents the battery from discharging. The battery would discharge because a reverse polarity protection relay is always activated when the battery is connected, and the holding current of the relay discharges the battery over time. To switch on the training stand, always switch on the battery isolator switch first and then the ignition. This is important because the simulation electronics must always be supplied with voltage before the ESC system itself is switched on. Otherwise, error messages may appear. If the engine should be started after the ignition has been switched on, the ignition key must be turned to the right to the start position until the engine has started and an engine noise can be heard. The braking process is triggered by actuating the brake lever. Actuation of the brake is indicated by the brake light. The training stand can now be used for the various experiments. To do this, the training stand is switched off again and restarted for the test sequence. First, it is checked whether the ignition key is in the left-end position. This ensures that the ESC is not supplied with voltage after the battery isolating switch has been operated before the simulation microcontroller has started, and provides the ESP with plausible operating values such as yaw rate, lateral acceleration, etc. The accelerator pedal potentiometer should be in the left-end position, idle position. The training stand allows the simulation of electrical malfunctions. This mainly concerns sensor errors such as the failure of wheel speed sensors or pressure sensors, etc. A fault switching device can be connected to the corresponding socket on the front panel. If no fault switching device is connected, a jumper plug must be used. If there is neither a fault switching device nor a jumper plug, the training stand is not functional. The next step is to operate the battery isolating switch and supply the training stand with voltage and wait a short moment until the simulation microcontroller has started. The ignition can now be switched on and the training stand is ready for use. Turning the ignition switch to the right start position starts the engine and an engine noise can be heard. The virtual vehicle can be accelerated by slightly turning the accelerator pedal potentiometer. If the vehicle is in motion, the steering is first set to straight ahead. The yaw rate display can be used to tell whether the vehicle is cornering. The luminous point of the yaw rate display stands still when the vehicle is driving straight ahead. Now the vehicle can be accelerated to its top speed by slowly accelerating. Demonstration of the ALB function. As already mentioned above, the ESP contains several subsystems. One of these systems is the ALB, anti-lock brake. The function of an anti-lock brake control is a technical standard that has been in place for some time. Depending on the wheel deceleration, tendency to lock, or wheel re-acceleration, the brake pressure effective on the wheel brake cylinder is reduced, maintained or increased again. In addition to brake pressure regulation depending on the wheel acceleration values. There is a control intervention depending on the brake slip. The control intervention, which is dependent on the wheel slip, optimizes the braking force transmission and ensures sufficient tracking forces, within the framework of the physical laws, for steering the vehicle. When cornering too quickly, ALB cannot prevent the vehicle from braking away either. The intervention to control the braking force takes place for each wheel via two-way valves, which each increase, hold and decrease the effective brake pressure. The brake intervention takes place down to a minimum driving speed of approximately 12 km per hour, to demonstrate the ALB behavior. The brake pressure curve can be displayed as a continuous line graphic on 4 displays, assigned to the wheels. The display instruments must be set to the appropriate display type. To do this, tap with your finger in the lower left corner of the screen until the line graphic is visible. Demonstration of the braking process. In the first attempt at braking, the tire is braked within the limits of its grip. The ALB does not trigger any control intervention. In the second braking attempt, the tires braked so hard that the available frictional forces are no longer sufficient. The ALB causes a control intervention and modulates the brake pressure in the wheel brake cylinders. First, a slight braking. No ALB control intervention. Now a much stronger braking. The ALB control intervention can be clearly seen and heard. Excessive acceleration causes EDL and ASC intervention. Depending on how impulsive or how strong the braking is, it can happen that the ALB reacts with a fault message and terminates the ALB control. In this case, the ignition is simply switched off during operation, switched on again, and the engine restarted by turning the ignition switch to the right. The braking tests can, for example, be repeated several times with different driving speeds and braking forces in order to understand the functional behavior of the ALB control. Demonstration of the ESC function. The ESC system, electronic stability control, requires various senses to ensure that it functions correctly. A steering angle sensor transmits the steering angle of the steering wheel at the training stand to the ESC control unit. Several turns of the steering wheel are recorded. The ESC receives the information about the desired direction of travel, target course, from this sensor. Without the steering angle information, the ESC function fails. The steering angle information is reported to the ESC control unit as a CAN bus message. A lateral acceleration sensor informs the control unit of the vehicle's tendency to swerve. If the vehicle is moving through a curve at a certain speed, the theoretical lateral acceleration must be measurable. If the measured lateral acceleration is lower, the vehicle understeers and tends to brake out of the curve. If the lateral acceleration approaches a critical value at which there is a risk that the guidance forces are no longer sufficient to keep the vehicle in the lane, the ESC control unit reduces the engine output and thus the cornering speed. There is no original lateral acceleration sensor installed on the training stand. A microcontroller continuously calculates the resulting theoretical lateral acceleration from the driving speed, steering angle and vehicle wheelbase and reports this as a signal voltage between 0 and 5 volts to the ESC control unit. A yaw rate sensor records the rate of rotation of the vehicle around the vertical axis. From the vehicle speed and the steering angle, reported by the steering angle sensor, the control unit determines the target travel path of the vehicle and from this the theoretically expected yaw rate. If the yaw rate reported by the yaw rate sensor deviates significantly from the calculated yaw rate value, the ESC control unit detects oversteering or understeering behavior and the ESC control unit intervenes. The type of control intervention, which wheel has to be braked, is a reduction in engine drive torque necessary, etc., depends on the actual vehicle condition. A master cylinder brake pressure sensor reports the current brake pressure in the brake circuit to the control unit. From this, the ESC determines the wheel braking forces and thus the longitudinal forces that act on the vehicle. In the event of a control intervention, this value is also used to determine the available cornering forces. How much can you brake without exceeding the available cornering forces? Without the signal from the brake pressure sensor, the ESC system fails. In order to show the reaction of the ESC to driving instabilities, left and right turns are driven, and disturbance variables such as under or oversteering are entered at the push of a button. It should be observed on which wheel the ESC tries to stabilize the vehicle again by means of targeted braking. In order to be able to demonstrate a typical dangerous situation, a curve must be initiated before the actual attempt. To do this, for example, the steering wheel is slowly turned to the right to make a right turn. Half or 3/4 of a turn of the steering wheel should be enough. If the driving data theoretically calculated by the ESC matching the sensor information, then there is no control intervention. However, if a fault is entered, in this case oversteering, the ESP reacts with a control intervention. If, for example, an oversteer fault is triggered, the fault can be recognized very well by the sudden increase in the yaw rate. The slip angle is one of the most important vehicle variables in vehicle dynamics control. If this takes on too high values while driving, the driving situation is viewed as critical. With very high side slip angles, it can be assumed that the vehicle may be at an angle to the direction of travel and can hardly be controlled. The slip angle is determined, in simple terms, based on the measured lateral acceleration, vehicle speed and yaw rate. When the disturbance is triggered, the lateral acceleration reported by the lateral acceleration sensor is reduced so that it is lower than the theoretically expected lateral acceleration. The ESC reacts to this with a brake intervention in order to reduce the slip angle and thus the inclination of the vehicle. In further experiments, the direction of the curve, left or right curve, can be changed and an oversteer or understeer disturbance can be entered alternately. If the braking control intervention is observed, the functionality of the ESC becomes clearly understandable. Through various experiments with the training stand, the trainee gets a feeling and understanding of how the ESC works. Measurement circuit diagrams can be connected to the training stand, which allow the trainees to carry out various electrical measurements within the wiring of the ESC system. Up to 8 panels can be connected at the same time. These plates can be used universally and are adapted to the system to be examined by means of a perforated paper mask on which the respective circuit diagram is printed. In order to use this measurement option, at least one circuit board, a 37-pin ribbon cable and the associated circuit diagram paper overlay masks are required. If only the minimum equipment was ordered at first, the number of plates can be increased later without any problems. Since the trainees write down their measurement results on the paper masks, the trainees should take the paper masks with them to their work documents. For this reason, the paper masks can be reordered in 100 pieces as consumables. Student measurement circuit diagrams can be connected to this multiple socket. Up to approximately 8 circuit diagrams can be connected at the same time. The circuit diagrams have 2 sockets, one on the left and one on the right. It is thus possible to link several circuit diagrams with the associated multiple cables. First, plug the cable into the socket on the training stand. Then the other end of the connection cable is plugged into the circuit board. The second socket on the circuit diagram board can be used to connect additional circuit diagram boards. Once the cable connection between the training stand and the student measurement circuit board has been established, measurements can begin. The cable from the training stand to the first student measurement circuit board should always be a little longer so that the first student desk or working place can be reached. Following are some examples of voltage measurements in the measurement circuit diagram. Checking the voltage supply of the master cylinder brake pressure sensor. First, the ground connection. No significant potential difference can be measured between the sensor mass and the vehicle mass. Just a few millivolts, so fine. Now the supply voltage is checked. 5 volts should be measurable. The voltmeter shows the necessary voltage. So everything is fine here too. The brake control unit recognizes the initiation of the braking process, among other things, from the signal of the brake switch. Here it is checked whether the signal voltage of the brake switch is applied to the corresponding control unit contact. To do this, the brake is actuated several times. The vehicle must be in motion to check the signal of the lateral acceleration sensor. Without cornering, the signal level is approximately 2.5 volts. To change the sensor signal, the steering wheel must be turned alternately to the left and right. The strength of the signal change increases with increasing driving speed and steering angle. If the vehicle is driving straight ahead or if the vehicle is stationary, there is no longer any lateral acceleration and the sensor signal is again approximately 2.5 volts. The signal from the yaw rate sensor when the vehicle is not cornering is approximately 2.5 volts. In order to measure a signal change, the vehicle must be in motion and a curve must be steered. If the vehicle drives straight ahead again or if the vehicle is stationary, a signal level of approximately 2.5 volts can be measured again. Using the student measurement circuit diagrams, a wide variety of measurements can be carried out on the components of the ESC system. Fault switching device. The instruction of the trainees on mechatronic systems should enable them, among other things, to be able to maintain and repair these systems later in their professional activity. In order to be able to carry out a repair on a defective system, the fault must be localized. So an error diagnosis is necessary first. A fault switching device can be connected to the training stand for troubleshooting training. For this purpose there is a multi-pole socket in the front panel into which the connection cable of the fault switching device can be plugged. If no fault switching device is used, the supplied dummy plug must be inserted into this socket in order to enable error-free operation. There is a multiple plug on the cable of the fault switching device which is plugged into the socket on the training stand. Which fault should be switched and which fault the trainee has diagnosed is entered using the keyboard on the fault switching device. A key switch must be operated to enter errors in the error switching device. Only the trainer can enter errors with his key or delete diagnostic answers given by the trainee. Two light-emitting diodes, one green and one red, indicate the current operating status. Before connecting the fault switching device, the ignition and the battery isolator switch are switched off. If this is not done, the ESC control unit saves the errors that occurred during the time of plug change in its error memory. First remove the dummy plug. Then the plug of the fault switching device is plugged into the socket of the training stand. When the connection between the fault switching device and the training stand has been established, the battery isolating switch can be switched on first. Before the ignition is switched on, it should be checked whether any errors are still stored in the fault switching device. To check for existing errors, the key switch is turned to the right. If LEDs light up, they can be switched off by pressing the respective button. By turning the key switch to the left, any previously possibly set errors are deleted. The ignition of the ESC system can now be switched on. Following is an explanation of the error input in the fault switching device. The entry of errors, the deletion of errors and the diagnostic response of the trainees take place via 10 keys. An LED is assigned to each button, which provides feedback on the respective switching action. To enter errors, first turn the key switch to the right. The red LED lights up. By pressing the buttons 1 to 10 errors can be switched. An LED assigned to the key indicates a set error. Any number of errors can be set at the same time. A set error can be deleted by pressing the button again. If the key is turned to the left again, the errors are actually switched. The fault switching device is now in student response mode. Believes the student to have found an error. The corresponding button on the error switchgear is pressed. If the answer is wrong, the key LED flashes and a tone can be heard. In order to enable the trainee to answer, he or she needs a list of the errors that are assigned to the individual keys. The trainee selects the list entry that is correct for him and enters its number into the fault switching device. To delete the trainee's answers or to enter other errors, the key is turned to the right again. If the fault switching device is to be operated in examination mode, the instructor removes the key from the fault switching device after the fault has been entered, so the trainee cannot undo his answers. The fault-switching device can be used universally for a wide variety of BBH teaching devices. Each teaching device then has a suitable error list from which the trainee can select a suitable answer. A PC can be connected to the training stand for a better understanding of how the electronic stability system works. The scope of delivery of the training stand includes a USB cable and a PC program that can run under the Windows operating system. The PC program enables a clear graphic presentation of the ESC operating values, provides additional information and technical explanations, and allows written material to be printed out. There is a USB socket on the front panel of the training stand, which is intended for connection to a PC. The supplied USB cable is first plugged into the socket on the training stand. Then the other side of the cable is plugged into a USB socket of the Windows PC used. With the PC switched on, the supplied USB stick can now be plugged into a USB port on the computer. If the USB stick is recognized by the operating system, a signal tone may be audible, and depending on the default settings, the File Explorer opens. With a double click on the installation program, Setup EXE, the program installation is started. If necessary, select English as the program language. Start the program installation with the Continue button. The program to be installed should already be selected. After all program files have been copied, the interface driver has to be installed. To do this, first click the Interface USB Driver text field and then the Install button. After a short moment, the driver installation program starts. Depending on whether an older driver version was already installed, the old version is uninstalled first and then the new version is installed. After the driver has been installed, you can exit the installation program by pressing the Finish key. There is now a new icon on the desktop of the PC with which the program can be started. After starting the program, you are in the main menu of the program. Select the appropriate program language and move the mouse arrow, for example, over the various components of the training stand to obtain additional information. From here you can branch to other parts of the program. The operating values of the ESC system are displayed numerically on this screen page. This makes it easy to get an overview of the current operating status. It can be seen very well how the values for the yaw rate and the lateral acceleration change depending on the steering angle and the steering direction when a vehicle is in motion. If the vehicle is braked heavily, the change in color of the wheels shows where the brake pressure is being built up or reduced by the ALB intervention. In addition, the master brake cylinder pressure and the pressure in a wheel brake cylinder are displayed. Additional information can be displayed on the circuit diagram program page by hovering over the components with the mouse arrow. Other program items can also be accessed from this page. The ALB function in the event of excessive braking, when the grip limits of the tires are exceeded, can be shown in this part of the program. During the braking process, the master cylinder pressure, the wheel brake cylinder pressure, the driving speed and the speed of a braked wheel are shown as a line graphic over time. It can be seen very clearly that the wheel cylinder pressure is not constant despite the constant master brake cylinder pressure. The ALB system modulates the brake pressure effective in the wheel cylinder depending on the current vehicle condition. If the brake is released again, the vehicle accelerates to the top speed dependent on the accelerator pedal. Returning to the circuit diagram, for example, the ESC function can be examined. The steering angle, yaw rate, lateral acceleration and engine power are displayed as a line graphic. On the right under the line writing, a symbolic car is shown where on its four wheels the braking intervention is visualized. The steering direction is shown by a small red arrow. If the vehicle drives a curve and the understeer or oversteer fault is triggered, the ESC system brakes the wheel, which either supports cornering or reduces the yaw rate around the vertical axis and thus the oversteer behavior. It can also be seen that the ESC reduces the engine power when oversteering. Back to the circuit diagram, the program part with the display of the wheel sensor signals can be called up. The signals from three sensors are shown at the same time. The oscilloscope can be triggered on the first channel, wheel front left. In this way, speed differences between the wheels can be recognized by the signal flow. The signal form corresponds to that of Hall sensors. However, it is not the signals from original sensors, but these signals are simulated electronically. Back in the circuit diagram program page, further menu items can be called up. For example, if you click on the circuit symbol for the lateral acceleration sensor, you will be taken to a program page where the functional principle of this sensor is explained. If the vehicle moves alternately to the left and right, a changing lateral acceleration can be recognized from the schematic representation of the sensor. This was just a brief overview of the program to give an idea of the possibilities. If the program has been closed again and should then be restarted later, it must be ensured that the USB connection from the PC to the training stand must always be established first, and only then can the program be started. Otherwise the PC program cannot recognize the training stand and no values are displayed.